We've described most of the functions, if not all of the functions we've worked with so far in the course, in terms of the standard y equals f of x. Now that's great and has gotten us a lot of mileage, but some curves can't be described by that form y equals f of x. So an example here is something that contains a loop like this. Now the reason it can't be described by y equals f of x is that it fails the vertical line test. If you were to draw a vertical line, a function cannot have more than one output for a given input. And you see that if I draw a vertical line, it corresponds to an x value, and in a loop like this, there are several y values that come up. Now, branches like physics and other branches of science need us to be able to describe curves like this. So for instance, if a bug or a fly, flies in this pattern, they don't care about the vertical line test. They're moving in this way, and physics wants to be able to describe the path of such an object. So how are we going to describe these curves mathematically? Well, we are going to take inspiration from physics again. We are going to construct functions. We are going to give functions for x and y separately. And in physics class, you do this anyways. You separate the x direction of motion from the y direction of motion, and then we are going to make them depend on a parameter. And I'm going to call it t for time, but mathematically there's no reason that it needs to be time. It's just some other parameter that they depend on. So if you take a look at this curve, what we're saying is that at any point along the curve, you are going to specify coordinates, x of t and y of t. Now, this could be at some time t1, and then there could be another point, x of t2 and y of t2, and so on and so forth. So what ends up happening is that if you were to think about this now in terms of time, you could trace out this path in terms of time. So it would be like watching a movie of a little bug or an object flying around, and if you were to tell it different times, it would tell you different locations in space. So the input here would be time values, t, and then the output would be position, the x and the y coordinates separately. And in this way, each of x and y are a function of time. But what it doesn't prevent you from doing is being in the same position in space at different times. So this type of description is a lot more flexible. It allows us to deal with things like loops and curves and closed circles and things of that sort, because you can trace them out at different points in time, and you may end up with the same point in space. So this is what is called a parametric description, because it depends on the parameter t. And what you end up getting is a parametric curve. The equations, the parametric equations, would be x of t and y of t. And so what ends up happening is that, again, these are each functions of time. So just like in physics class, when you talk about projectiles, you separate the x behavior and you get x as a function of time, and you separate it from the y behavior and you get y as a function of time. Now this is great. What we're doing in this first lesson here, this first video, is just trying to get a sense of how these parametric equations work and what you see when you have a set of parametric equations. Now, they're usually coupled together with a brace like this, and you have to be given limits on the time value, the t value. So the idea here is that we want to specify when this curve will take place, and we will figure out where it takes place. And so we'd like to be able to graph this. Now, there are a lot of different ways to do this. The easiest by far is to go and use Desmos. Now, in Desmos, all you have to do is type these equations in as coordinates of a point. So you'd have x of t, comma, y of t. So all you need to do is type in your x equation, your y equation, and underneath it will give you a little section to restrict t. And if you do that, it will automatically plot it. So it's about as simple as it could possibly be. Now, we'd like to get a little bit more understanding in terms of how do you do this by hand? Because the ideas that come up when you do it by hand are also useful, and they give you a little bit more insight. Now, the simplest idea is we are going to make a table of values. So we're going to go right back to where we were in the beginning of functions. This time the table is a little bit more involved. You're going to choose input values for for t, and you will get back your x values and your y values. So they each depend on t. Now we have been given a range of t values from -2 up to +3. I'm just going to pick these convenient values of t in jumps of 1 and fill things in from there. The x dependent is very easy. It's just take the value of t and add 1. So there's not a lot of thought that needs to go into this. It's easy enough to come up with these points. The y values are a little bit more involved, but nothing too bad. So if you just sit there and think about it, very easy to come up with the results. Now what we do is we say, okay, when t is equal to when t is equal to -2, we should be at the point 1, -9. When t is equal to -1, we should be at the point 0, 7. And so all we do is we end up with a table of values that has an extra layer of information. And the extra layer of information has to do with when. So it's not only do we get where, we also get when. So we graph a standard Cartesian axis like we normally would, and we'll take our jumps as we normally would. The y values are going to be a little bit different, but nothing out of the ordinary. And my apologies for this messy looking graph, but you'll get the idea. So all we now do is go ahead and plot these points in. So at time -2, I should be at an x value of -1, and y is 9. So I have a dot that lives somewhere around there. When I'm at the time of -1, I should be at 0 and 7, so somewhere around there. When I'm at time 0, I should be at the point 1, 5, so somewhere around there. The next point lives at 2 and 3, so somewhere around there. And then you can see how the rest are going to shake out. I'll be at 3 and 1, and then at 4 and -1. So just like with any graphing, what we're doing is collecting a certain number of points, and then we make a guess about how to connect the dots. Each of these functions we've been given is continuous. They're just linear, so there should be nothing strange going on. No holes, no gaps, no jumps, no breaks. So if we just play connect the dots, what we end up with is a line segment. Now I've drawn it poorly, but you get the idea. And not only do we get points in space, we also get direction in time. So if we were to watch a movie of this, we should start up here and then proceed down the line till the bottom. So when you take a program like Desmos or any sort of calculator that graphs things, this is how it effectively does it. It just plots points and it goes from there. Now, another method is something called eliminating the parameter. When I look at this result above, it looks so simple. It just looks like a straight line. In fact, I would love to know the Cartesian equation of this line, because it looks like something like this would be able to be graphed as a function. So this is a special case when we can get y equals f of x. We won't always be able to get this, but sometimes we can. What you do is you take your equations. We've got our x of t and we've got our y of t equation. And what you can do is essentially do what the title says, eliminate the parameter. So you can solve one of these equations for for t, and then you can sub it into the other equation. So you'll get y is 5 minus 2 into x minus 1. And if you just go through and you do the algebra in that sense, what you'll find is that you end up with an equation that should match what your picture has done, or what your picture has given you. So if I take a look at this, this tells me I have a line, y equals 7 minus 2x. So the y-intercept should be 7, which it is right up here. And we should have a slope of -2, which in fact we do. Every time we move over one step, we drop 2. We move over one step, we drop 2. So this does match what the parametric graph gives you. Now, the Cartesian equation is great. It gives you a little bit of intuition, but the parametric form, or the parametric equations, give a direction in time. And this is lost when you eliminate the parameter. So if you try to eliminate the parameter to more easily graph it, you will lose this information. Now, this kind of thing also really comes to bear in these special situations. So for instance, if I were to give you x is the cosine of t and y is the sine of t, if I were to give these parametric equations, I would love to see what this produces. Now I can eliminate the parameter here, and I'll do that by using this kind of special trick. X squared plus y squared gives me cos of t squared plus sine of t squared, and I know that that has to be 1. So the Cartesian form gives me x squared plus y squared equals 1. This is a unit circle that has a radius equals 1 and a center of 0, 0. So what this result is telling me is that this set of parametric equations produces a unit circle. At any point on the circle, the coordinates are functions of time. So I've got where I should stand, but I don't yet know when I should be there. So I need directions in time. So I'm just going to pick some convenient values of t. So when t is 0, I should have x of 0 is the cosine of 0, which is 1, and y of 0 is the sine of 0, which is 0. So that tells me I should be at the point 1, 0 at the beginning here. So at time 0, I am right there. Now I can pick another convenient point. Let's say t is pi over 4. So x of pi over 4 is going to give me cos pi over 4, which is 1 over root 2, and y is going to give me exactly the same thing. Sine of pi over 4, which is 1 over root 2. So I know that I should be at the point right about here. 1 over root 2 and 1 over root 2. And this is at time pi over 4. And so if you just take a couple of points like this, you can determine a direction. And so the direction here is going to be counterclockwise. As time evolves forward, you will move around this circle in a counterclockwise direction. Now, that information is buried in to the Cartesian equations, into the parametric equations. But what happens is that you can end up with many different ways of traversing this circle through different parametric forms. So for instance, if I were to tell you cosine of 2t and sine of 2t, this will also produce a unit circle. I'll get cos 2t squared plus sine 2t squared. This will still be 1. It doesn't matter what the argument on the inside is. We will still get a unit circle. But there's going to be a difference as compared to what we did above. If we wanted to talk about the direction again, if we were to ask about time 0, we would still get the point 1, 0 at the beginning here. So there's our time 0 time. But if we were now to put in pi over 4, we would get that x of pi over 4 is the cosine of pi over 2. Remember, there's a factor of 2 on the inside. So that would be 0. And y of pi over 4 would give us sine of pi over 2, which would be 1. So that means at time pi over 4, we have gone further. So we are still going counterclockwise, but our period is doubled. Or sorry, our period is halved. We move around twice as fast. So it's going to take me half as much time to go around this circle as it would have before. And if you understand this, you can do all sorts of different things. So for instance, if I were to switch the sign of the term on the inside and switch things around in this way, we would switch the direction. The direction now would be clockwise, but we would still have a unit circle. So the parametric equations hold a lot of information for us. If we need to graph or visualize these parametric equations, we can make a table of values. Sometimes we can eliminate the parameter to get a good picture. We just have to be careful to bring back that directional information with respect to time. Of course, the most straightforward thing is to use Desmos. Now, in the next video, we're going to take a look at some basic calculus regarding parametric curves.